Hi, I'm Brian Brightbill, and in this MCAT Science Review video, we'll be observing the processes of membrane transport. To do this, we'll be looking at concentration gradients and analyzing passive transport, facilitated diffusion, active transport, and endocytosis and exocytosis. By the end of this video, we want to be able to categorize the different types of membrane transport, identifying what type is used to move any specific particle across the membrane. This content is not necessarily the most difficult on the MCAT, but that means that the MCAT will be testing it in trickier, more thought-provoking ways. We should expect to see it applied in various processes throughout the biological systems, including the movement of pyruvate across the mitochondrial membrane, exocytosis of neurotransmitter in the synapse, and even how oxygen moves into the cell and carbon dioxide moves out. This will allow us to be able to answer questions like the one at the bottom of your screen regarding what is used to move sodium across the membrane. Before we can start looking at the specific membrane transport processes, we have to look at the overall change in energy state that leads to them being spontaneous or non-spontaneous. This is represented through the change in Gibbs free energy, or the delta G. This is the same Gibbs free energy as we see in general chemistry and organic chemistry. In processes with a negative delta G, the energy level of the system is going down, and this is a favorable, spontaneous process, meaning they do not require the input of outside energy. On the other hand, are positive delta G processes, where the energy level of the system is going up. So there must be an input of outside energy, and these processes are called active. In order to determine whether or not a process is spontaneous or non-spontaneous, it's helpful to have an equation to evaluate this. Here we use the equation delta G equals delta H minus T delta S, just like in general chemistry. Here the delta G is for Gibbs free energy, the delta H is for change in enthalpy, T is for temperature in Kelvin, and delta S is for entropy. When these terms result in a positive Gibbs free energy, it results in an active process. This means that energy is required, and that will depend both on the temperature and the energy that is already provided by the enthalpy change of the system. On the other hand, if the process provides a negative delta G, it is a spontaneous process. In these cases, entropy is the motivator. It is the source of energy for the process. And this also means that an increase in temperature will cause passive processes to occur more quickly. We'll be looking at active transport processes soon, but first let's apply this information to passive processes. In passive processes, the entropy supplies the energy in the form of a concentration gradient. As that concentration gradient is dispelled, the system becomes more disordered. Becoming more disordered is something favorable. The simplest example of this is simple diffusion. In these cases, something that's permeable is able to move across the membrane, and so it will move down its own concentration gradient. In this case, we can see that we have some permeable solute with a high concentration above and a low initial concentration below the membrane. Because they can move across the membrane, and this concentration gradient is a form of stored energy, we will have net movement as we move from high concentration to low concentration. This movement will continue until either side of the membrane has equal concentration. At this point, the energy provided by the entropy change of the system has been used up, and we have equal concentrations on either side. This does not mean that there is no movement from one side to the other, but it does mean that there is no net movement. It is a dynamic equilibrium. Once again, another concept that we see in chemistry with equilibrium and equilibria constants. Except in these cases, instead of molecules breaking down or combining, we're moving particles across a membrane. And then there's the specific type of diffusion called osmosis. Osmosis is diffusion that is specific to water. Osmosis will be very similar to the process of diffusion that we just saw. When a cell has equal amounts of solute inside of it as exists outside of the cell is called isotonic. In these cases, even if the solute can't move across the membrane, the water can be moving back and forth, but once again in a dynamic equilibrium. The water can move into the cell and out of the cell, but there's no net change because water has no concentration gradient here. However, if we have a difference in solute concentration, that also necessarily means a difference in water concentration. Where solute is higher, the solvent, water, is lower. So if we have a hypotonic solution, and therefore a hypertonic cell, the water will move from hypo to hyper, up the concentration gradient of the solute, but that is down its own concentration gradient. It is moving down the concentration gradient of water. When this occurs, in this case, the cell is swelling, its volume is increasing, because water is moving in. And finally, if the reverse situation is true, if there's more solute outside of the cell, then the water will flow out towards the hypertonic solution outside of the cell. This removes water from the cell, making it shrivel, making its volume decrease. A trend we see on the MCAT is for questions involving the volume of cells to be answered by understanding the hypotonic-hypertonic relationship of the cell and its environment. As water is the solvent as opposed to the solute, there are some greater complexities and some greater points of interest for osmosis than there are for diffusion. One is the concept of osmotic pressure, which is how we measure the force causing osmosis to happen. In this situation, for instance, we can see that on the left we have higher concentration 0.1 molar sodium chloride, while on the right we have pure water, which would be a low concentration of solute. The water will flow towards the higher solute concentration, the lower water concentration, and will cause the water level on the left, which was initially equal, to rise. Now, even if this is pure water on the right side, it won't rise indefinitely. Eventually, there will be enough hydrostatic pressure on the left side above the level of the water on the right side that physical hydrostatic pressure will prevent further osmosis from occurring. That hydrostatic pressure against the flow of water through osmosis is how we measure osmotic pressure. This value can be calculated using this equation. Here we see pi equals ImRT. In this case, capital Pi is the osmotic pressure. I in this equation represents the Van't Hoff factor, as osmotic pressure is a colligative property. The Van't Hoff factor represents the number of particles that dissociate into solution. For instance, for sodium chloride, the Van't Hoff factor is 2, whereas for glucose, the Van't Hoff factor is 1. M is for molarity, in moles per liter. R is the ideal gas constant, as we see show up in other places throughout chemistry, including the gas laws and the Nernst equation. And T is for temperature, in Kelvin. In simple diffusion and in osmosis, the only requirement was permeability to the membrane. But now as we move on to substances that are impermeable either because they're too large or polar or they're ions, they're not able to cross that membrane freely. In these cases, a membrane protein is required to help them across. One type of protein that can be used to transport impermeable solute across the membrane are protein channels. Those protein channels can be either opened or closed and can switch back and forth depending on a variety of signals. On the other hand, carrier proteins work a little more like revolving doors. When a solute enters them from one side, it will induce a shape change that will cause the protein to close to the side from which the solute entered and then open to the other side. But this means that the carrier will only be open to one side of the membrane at a time. And in between being open to one side and the other side, it will be in the occluded state, where it is temporarily not open to either side of the membrane. Overall, for both protein channel facilitated diffusion and facilitated diffusion through carrier proteins, no other input of outside energy is required because there is a concentration gradient of solute that is the source of energy. On the other hand, there are times when the membrane needs to move materials against their concentration gradient. The most common method for this is primary active transport. Primary active transport is a mechanism that uses ATP as the energy source, replacing the increase in entropy that diffusion, osmosis, and facilitated diffusion made use of. For primary active transport, we name the membranes that accomplish this transmembrane ATPases. Let's look at an example of an ATPase that moves sodium. In this case, we can see sodium binding into the protein, and then ATP coming along to provide that energy. When the high-energy ATP phosphate bond is broken, ADP and inorganic phosphate are released, and so is sodium against its concentration gradient, in this case into the extracellular space. On the other hand, there are times when active transport can make use of the energy from the concentration gradient of another solute. In these cases, we're back to using entropy as our driving energy source. In this example, sodium is now providing the energy gradient. Sodium wants to move downward into the intracellular space here, and will bind into the protein. Meanwhile, an amino acid binds from the other side to go against its own concentration gradient, and the two switch, moving the amino acid into the extracellular space. And because in this case, the sodium and the amino acid moved in opposite directions, this is referred to as an antiport mechanism. The solute providing the energy moves opposite the direction of the particle being moved up its concentration gradient. There are cases when they can flow in the same direction, and that is known as symport. In all of the processes we've seen thus far, the result is that the solute crosses the membrane. However, in the case of endo and exocytosis, a vesicle is formed or released from the membrane. These processes are used to move things that are just too big to move across the membrane through a protein, or there's too much to move efficiently in any other way. In endocytosis, the cell membrane invaginates and pinches, forming a bubble which we refer to as a vesicle. That vesicle contains the extracellular fluid as well as whatever solute the cell wanted to bring in. We will see the terms pinocytosis and phagocytosis used for this, as pinocytosis is the cell intentionally bringing in fluids and dissolved particles, and phagocytosis is when the cell brings in large solids. And this is an important process in the immune system, as this is how white blood cells destroy infectious material. Then when the cell wants to move large materials or large quantities out, the process of exocytosis takes the vesicle containing those materials, merges it with the membrane, and expels the material into the extracellular fluid. This is that example that was incredibly important at the synapse, as this is the way that neurotransmitter is released into the synapse from the synaptic terminal of the neuron. Now let's take a moment to practice applying these concepts. Go ahead and choose your answer for question number 1. The correct answer is B, facilitate diffusion. In the question, we are asked to move sodium ions across the cell membrane without using energy. To move sodium ions, which are impermeable, we need a protein, which means that the answer must be either facilitate diffusion or active transport. Facilitate diffusion of the two is the one that does not require energy, making B, once again, the correct answer. Now take a look at question number 2 and choose your answer. The correct answer to this one is B, antiport. Because we are using the energy from the gradient of sodium to move another ion, this must be secondary active transport. And because the ions are moving in opposite directions, it must be antiport, B. Now let's review the highest yield material we've gone over. The first process is simple diffusion, wherein small nonpolar particles, like carbon dioxide and oxygen, are able to move across the membrane down their own concentration gradient. Next is osmosis, wherein water moves down its concentration gradient against the concentration gradient of solute. And next is facilitate diffusion, where we are once again moving the particle down its concentration gradient, but here the particle is impermeable, so it must go through a protein channel or carrier protein. And in the process of active transport, we're moving particles against their concentration gradient. In primary active transport, we use ATP, which uses the energy from its high energy phosphate bond to become ADP, moving the particle against its concentration gradient. We are also able to use the concentration gradient of other particles in order to provide that energy, and this is known as secondary active transport. In endocytosis, we invaginate the cell membrane to capture some of the extracellular fluid and some of the particles in it, and bring it in the form of a vesicle into the cell. In exocytosis, we bring that vesicle to the cell membrane, and it opens it and releases its contents into the extracellular fluid. Thank you for joining me, and best of luck to you on the MCAT.